Hey everyone, you are watching AG Maths Academy. Welcome back to the channel. In today's video, we will be solving some important questions from CC-5 paper of 2021. This paper covers questions from limits, continuity, differentiability, which are fundamental topics in calculus. So, whether you are preparing for exams or just want to strengthen your understanding, this session will help you grasp the concepts with clear explanations and step by step solutions. So, grab your notebook and let's get started. Question number 3b applies Sandwich theorem to evaluate the value of this limit. Okay, limit x tends to 0, 1 plus x whole to the power 1 by x. So, for this question, we're gonna evaluate the right hand limit first. Okay, then we're going to evaluate the left hand limit. So for the right hand limit, first I take let x equals to 1 by y. So as x tends to 0 plus, okay, then y tends to infinity, positive infinity. So from here we get this limit equals to limit y tends to infinity 1 plus 1 by y to the power y. Okay, so now to evaluate this limit, okay, we're gonna take this sequence. Okay. This sequence actually a convergent sequence and it converges to E. So we can write that limit n tends to infinity 1 plus 1 by n equal to E. Okay. So now here, like, n obviously belongs to n belongs to natural number, the set of all natural numbers. So now we're gonna evaluate this from here. Okay. So for that, as y tends to infinity, okay, so the value of y is getting bigger and bigger and bigger towards positive infinity. Okay, so now for this we take y greater than 1. Okay. So now actually we can start using this. Let mod of y equals to k. So from here we can write that k plus 1 less than y equals to no, actually k greater equals to y uh, less than k plus 1. Okay. So now from here we can write that 1 by k plus 1 1 by y 1 by k 1 by k plus 1 1 by y 1 plus 1 by k. Now from here, like as k is less equals to y and y is less than k plus 1, so from here we can write that 1 plus k plus 1 to the power k is less than 1 by y to the power y 1 plus k to the power k plus 1. Okay. So now what do we get? So now we're gonna evaluate this now as so what we have taken like mod of y is equals to k. Okay. Now we can say that as now y tends to infinity, k also tends to infinity. Okay. So now we can write that from here limit k tends to infinity 1 plus 1 by k plus 1 to the power k limit now we are introducing the limit, so this inequalities will be less equal. Okay. So now to apply Sandwich theorem, what we're going to do is we're going to evaluate this limit and we're going to evaluate this limit. Okay. So now if the value of both of these limits are equal, so we're going to evaluate these two limits, and if we get that these two limits are equal, then by Sandwich theorem you can say that the middle one will also be equal to these two limits. Okay. So first we need to evaluate this. Okay, so now we are evaluating this. So for this, we will take k plus 1 to the power k plus 1, okay, by 1 by 1 plus 1 by k plus 1. we have taken plus 1 here, and this will be to the power minus 1 of this. So actually this is same as the previous one. Now we can write that limit k tends to infinity k plus 1 by limit k tends to infinity okay. So now for the upper portion we can write that as k tends to infinity, k plus 1 will also tends to infinity. So now if we put like k plus 1, let's say it's u, okay, so this limit will be limit u tends to infinity 1 plus 1 by u, this will be u, and this will be okay. Now this, as we have taken like equals to k, so where k is actually a natural number, okay. So this will be e, so this will be e as limit n tends to infinity 1 plus 1 by n to the power n is e. So this will be e, and if we put k equals infinity, this will be so now if we put k equals to infinity, this will be 1 plus like infinity, this will be 1 plus 0, so this will be 1, okay. So this will be 1, and the whole thing, or rather this limit, will equals to e. So this is done. Now we're going to evaluate limit k tends to infinity 1 plus 1 by k 1 plus k, okay. So this will be k tends to infinity to the power k into 1 plus 1 by k, okay, and this will be limit k tends to infinity 1 plus 1 this into limit k tends to infinity this, okay. Now from here, or we can straight up write that this equals to e as limit n tends to infinity 1 plus 1 by n to the power n equals to e, okay? And k belongs to n, okay. So this will be e, and if we put k equals to infinity, this will be 1 plus 1 by infinity, which will be so this will be 1 plus 1 by infinity, this will be 1 plus 0 equal to 1. Okay, so the whole limit will be e into 1, which will be e. Okay, so this will also be e. Okay, so the inequality was, or rather the relation was, this limit k this equals to limit y tends to infinity 1 plus 1 by y to the power y, this one. Okay, so now we get that both of these limits is equals to e. Okay, then by sandwich theorem, we can write that this middle one, limit y tends to infinity 1 plus 1 by y to the power y equals to this one, e. So we get limit y tends to infinity 1 plus 1 by y to the power y is equal to e. From here, what we have taken before, we have taken that is x equals to 1 by y. Okay, so this will be limit x tends to 0 plus to e. So we get the right hand limit. So now we're going to evaluate the left hand limit. So limit x tends to 0 minus 1 plus x 1 by x. Okay. So for this, put x equals to 1 by y, as x tends to 0 minus y will tends to minus infinity. Okay, so this will be limit y tends to minus infinity to y. So from here we're going to put y equals to minus z. Now as y tends to minus infinity, z will tends to, so this will be minus infinity minus z, will be actually z equals to infinity. So z tends to infinity. Okay. Mm, so this will be limit z tends to infinity 1 minus 1 by z. This will be minus z. Okay. We limit z tends to infinity z minus 1 by z to the power minus z. This will be limit z tends to infinity. Okay, as it is to the power minus z, this will be, as it is z minus 1, it will be z by z minus 1 to the power z. So now we're gonna put this one z minus 1 also, let's say t. So now as z tends to infinity, so t tends to infinity. So this becomes limit t tends to infinity. This will be 1 plus t and this will be t and this will be 1 plus t. Okay. So this will be limit t tends to infinity 1 plus 1 by t 1 by t. Okay, then this equals to limit t tends to infinity 1 plus 1 by t to the power t. Okay. As it's 1 plus t, so it will be this multiplied by this. Now now if we put t equals to infinity here, this will be, so this will be 1 plus 1 by infinity, which is 1 plus 0, which is 1. Okay. So this will be 1 into, and this will be e. Okay. So the whole thing will be e. Okay. So now y is equal to e, as limit n tends to infinity n plus 1 by n to the power n equals to e. That's why it's equal to e. So it's 1 into e is equal to e. So this equals to e. Finally, we can say that this was our left hand limit. So x tends to 0 minus 1 plus x 1 by x equals to e. So now finally we can say this. Okay. So now the left hand limit is equals to E, and also the right hand limit is also equals to E. So now you can say that limit at 0 is also equals to E. So this is equals to E. Question number 7b. Examine uniform continuity of cos 1 by x on open 0, 2. Okay. So we need to prove that cos 1 by x, like, is it uniform continuous on 0, 2 or not? Okay. So actually we're gonna solve this problem in two different ways. So for the first approach, we're gonna use a theorem which is if is uniform continuous on an interval, let's say it's d, and if for every two pairs of sequence un and vn in D. So with we're taking two sequences in D such that un and vn, mod of un and vn, so it's actually tends to 0. That means limit un vn is equal to 0. But for this, if we get limit n tends to infinity f of un minus f of vn is equal to 0. So like mod of un minus vn tends to 0 implies mod of functional value of un minus functional value of vn tends to 0. So this is the first approach. So this is actually not uniform continuous on this region. So we're gonna show that we will take two sequence in 0, 2 such that limit un minus vn will be 0, but limit mod of f of un minus f of vn will not be 0. Let's take two sequence. Let's take xn is 1 by 2n plus 1 by 5, okay, and yn which is 1 by 2n plus 2 5, okay. So now and they both belongs to, okay, so both of the sequence belongs to a 0, 2. This is xn and yn. These sequences are from this interval. Now this will be 1 by 2n plus 1 pi minus 1 by 2n plus 2 pi. Okay, now we get that pi 2n plus 2 minus 2n minus 1 by 2n plus 1 2n plus 2. So this will be 1. So this will be 1 by pi 1 by 2 of this. Okay, so now uh, so now we get that so now what do we get? Mod of xn minus yn is equals to this one. So now limit n tends to infinity, this will be this will be infinity into the both, like it will be 1 by infinity and it will be 0, so this will be 0. So we get this one. Now we will try to find value of this. Okay, so this will be cos of we have taken that xn is equal to 1 by 2n plus 1 pi and sequence yn is equals to I actually forgot to mention that, like this n, like 2n plus 1 and 2n plus 2 here, where n belongs to n set of natural numbers. Okay, this is very important. I actually forgot to mention this before. Now what do we get? If x is actually cos 1 by x, so f of xn, this will be 1 by this, which will be cos 2n plus 1 multiplied by pi. Okay, and this will be cos of 2n plus 2 pi. Okay, so now this gives minus 1 and this gives 1, so it will be minus 1 2. Okay. So value of this is 2. Okay, so obviously, okay, first let me show you guys that, like how I am evaluating this, like cos 2n plus 1 into pi plus cos 2n plus 2 into pi. So first we're gonna take the graph of cos x, which is like is actually sin x. Hey, sorry for the interruption. If you are finding this video helpful, make sure to hit the subscribe button and turn on notifications so you don't miss out on the future videos. Your support helps me keep making more useful content for you. Now, let's move on to the next question. This and this will be the graph of cos x. Now, see that mm, it's 0 degree here, it's 90, it's 180, it's 270, it's 360, it's 450, 540, and this will be 630. Okay. If we take n equals 1, this will give us 2 into 1 plus 1, which is 3 pi. So this will give us 3 pi, okay, which is 540. This will be minus 1. For n equals 2, this will give us 2 multiplied by 2 plus 1. This will be 5 pi. So this will be actually 900 degree, and it will also give us minus 1. Okay. So cos of 900 is minus 1. So this is going to actually give us minus 1. Okay. And for the value of n equals 1, this is going to give us actually 2 into 1 plus 2, which is 4 pi. Okay. So this will be here. So this will be cos 360 is this 1. Okay. For n equals 2, this will be cos 2 into 2, 4 plus 2, 6. This will be cos of 6 pi, which will be again 1. So this is going to give us 1. Okay. So that's why it's minus 1, and it's minus, and this 1. So just like mod of minus 2, and it is 2. Okay. So now we get this equals 2. So limit n tends to infinity will also be 2. Now what we can see that xn minus yn is tending to 0, but functional value of xn and functional value of yn, so this is not tending to 0. From here we can say that cos of 1 by x is not uniformly continuous on 0, 2. Okay. Now the second approach, method 2. So for this one, we are actually going to use a theorem, which is if is uniformly continuous on an interval, let's say it's d, then we can write that for every Cauchy sequence, let's say it's sequence un. So for every Cauchy sequence un in D, if the sequence f of un is also a Cauchy sequence. Okay. This will be in R, actually not in D. Okay. As f will be D to R. Okay. So the codomain set is R here. So un is a Cauchy sequence in D, and f of un will be a Cauchy sequence in R. Okay. Now let us take a sequence, say xn, which is actually 1 by n pi by 2. This will be 2 by n pi. Okay, so we take this sequence which belongs to D, not belongs to, in open 0, 2. Okay. So now this is a Cauchy sequence in open 0 to 2. Now xn is a Cauchy sequence in open 0, 2. Okay, so now we get xn is a Cauchy sequence in 0, 2. So now the condition was f of xn must be a Cauchy sequence in R. Okay. So like if f is uniform continuous on this interval and xn is a Cauchy sequence in 0, 2, like this interval, then f xn must be a Cauchy sequence in R. Okay. Xn is equals 2 by n pi. So again I forgot to mention that n belongs to set of natural numbers. Okay, this is actually very important. I forgot to mention that. I forgot to actually mention this. Now we're gonna evaluate that the first value of f of xn. Okay, so for n equals to 1, so for n equals to 1, what do we get? It will be f of 2 into 1 by pi, this will be f of 2 pi, okay, which will be cos pi by 2, which will be 0. So the first value will be 0. Okay. Now we're gonna evaluate the second value. For this should be x2, which will be 2 by 2 into pi. So this will be f of pi, no, actually this will be f of 1 by pi, okay, and this will be cos of pi, which is minus 1, okay, this will be minus 1. So now if we keep calculating these values, this will be 0, 1, 0, minus 1, so on. So as we have seen that sequence f of xn has this kind of points, okay, like 0, minus 1, 0, 1, 0, minus 1. So from here we can say that if the sequence f of xn is a divergent sequence, okay, why? As like it cannot converge to a single point, okay. So now by the theorem I have shown before, we can write that or what do we get? Okay, we get this sequence xn in 0, 2 or sequence xn is actually a Cauchy sequence in 0, 2, okay. But this sequence f of xn is not a Cauchy sequence in R. Okay. So from here we can write that f is not uniform continuous on 0, 2. Okay, so prove. Question number 4b. Give an example of a function f r to r such that f is continuous at 0 and has discontinuity of second kind at every other point in R. Okay. So we need to define a function, let's say f of x, such that it is only continuous at x equal to 0 and rest is discontinuous. So first we will talk about what is second kind of discontinuity. So second kind of discontinuity is at least one of the limits. This is the left hand limit. and this is the right hand limit. Okay. So what do we know? So x tends to limit x tends to a will be fx if this will be, so if actually if left hand limit is equal to the right hand limit. Okay, so now second kind of discontinuity is this limit, either this limit, one of, like at least one of the limits, this is the left hand limit, or the right hand limit does not exist. Okay, so now we will see the example. A function f r to r is defined by, so value of fx is x when x is a rational number and 0 when x is irrational. Okay, so this kind of functions where the function has like defined values for rationals and irrationals, like these kind of functions are actually a form of Dirichlet function. Okay. So what is special in this kind of function? Okay, so for this kind of functions, f is only continuous at when the rational, like the rational value will be equal to the irrational one at x equal to 0. Okay, so f is only continuous at x equal to 0. This is the speciality of this kind of functions. So now say like this will be x square and this will be 4. So for x being rationals, the value of fx is x square, and for x being irrational, the value of fx is 4. Okay, so then f is only continuous at this equal to this. X square equal to 4, so this will be plus 2 and minus 2. Okay, so f is only continuous at x equal to plus 2 and x equal to minus 2. Okay, so this is the speciality of Dirichlet function. Okay, now we don't need that here, we need x and 0. Okay, so f is continuous at x equal to 0 and has second kind of discontinuity at every other point. Okay, so now it is actually a two number question. One number is for the example and the other one number is for the proof. Okay, so we need to prove this. Okay, so I'm writing the function here. F is continuous at 0. First we're going to prove that. Okay. So we will prove that by using the definition of continuous function. Okay, it's not the definition of continuous function. It's actually the definition of like a function is continuous at a point. This will be equals to f of x, as 0 is a rational number, so it will be f of x equal to x. So f of 0 will be 0. This will be mod of fx. Okay, so now this will be mod of x when x is rational, and this will be 0 when x will be irrational. Okay, so now let us define epsilon, actually a positive epsilon. Then if we write this minus f of 0, if we write this like the epsilon we have taken, this will be greater than this if for all x belongs to 0 minus epsilon, 0 plus epsilon, if is continuous at 0. Okay, so by the definition we get if is continuous at 0. Like see, f of mod of f of x minus f of 0 is less than epsilon. Okay, for all x belongs to this region. Okay, so like neighborhood of 0 comma epsilon. So by the definition we can write f is continuous at 0. Okay. So now we will prove that like f has discontinuity of second kind at every other point in R. Usually we prove this kind of thing by using a sequential criterion. Okay, so let us take a sequence of rational points or rational numbers, whatever you can, right? Rational points. Let's say un, okay, such that un is less than c. Okay, okay, so first we need to define actually what is c. So here we will define let c belongs to R and c is not equal to 0. Okay, so c as we're going to prove that f is discontinuous at every other point except 0. So this c must be not equal to 0 for all n belongs to n. So for all natural numbers. Okay, so now limit n tends to infinity, un will be equal to c. Okay, so what we have taken here is a sequence of rational points un such that the sequence is like less than c, and this sequence un converges to c, that is limit n tends to infinity un is equal to c. Okay, now we're going to evaluate where does f of un converges. Okay, so limit n tends to infinity f of un. Now see f of un, where un is a sequence of rational points. Okay, so for rational numbers we have fx is equal to x, so this will be limit n tends to infinity, so f of un will be un, this will be un, and this is equal to c. Okay, so c, so f of, so we get un converges to c and f of un also converges to c. Okay, so now let us take a sequence of irrational numbers, irrational points, let's say vn. Okay, irrational points vn such that vn is less than c for all n belongs to n. Okay. And as before, this function also converges to c, so limit of vn is equal to c. Okay, so now we will evaluate where does f of vn converge. Okay, so f of vn, and here vn is a sequence of irrational points. So for irrational values we have f of x is equal to 0. So f of vn, as vn is irrational, this will be 0, so the whole limit will be 0. Okay, so now what do we get is there is two sequence un and vn in R. Okay. So actually I should have mentioned this before, that un and vn are from R. Okay. So yeah, un and vn in R such that they both converge to same limit. Okay, but these two sequences they converge to different limits. As f of un is converging to c and f of vn is converging to 0. Okay, so by sequential criterion we get, what do we get? Limit x tends to c minus of fx does not exist. So now why it's x tends to c minus here? Okay, now see, when I was taking uh, two sequences un and vn, I have mentioned there that un is less than c and vn is less than c. Okay, so these two sequences is less than c. Okay, so we are taking two sequences from like left hand side of c. So that's why its limit x tends to c minus of x. Okay. So now similarly we can prove that okay x tends to c limit x tends to c minus fx does not exist where c not equal to 0. Okay, so we can prove that limit x tends to c plus fx does not exist where c not equal to 0. Okay, so now what do we get? We get this does not exist, and also the left hand limit does not exist. Okay. So I have told you before that if one of these two limit does not exist, then this is a second kind of discontinuity. Okay. So if has second kind of discontinuity at every other point, in R except 0. Okay. Question number 7a. So that fx equals 1 by x square is uniformly continuous on closed a comma infinity for a being positive, but not uniformly continuous on open 0 to infinity. Okay. So for this question, first we need to understand what is uniform continuity, or what is the definition of uniform continuity. Okay. So it is for a pre-assigned epsilon there exists a positive delta such that for any 2 points x1 and x2 in I means the interval where we're trying to say that f is uniform continuous. Okay, so obviously x1 and x2 are unequal, so they are not the same point. So if x1 mod of x1 minus x2 is less than delta, this implies mod of f of x1 minus f of x2 which is less than epsilon. Okay, so see that we are choosing the epsilon. Okay, so it is for a pre-assigned or chosen epsilon. Okay, so we get that mod of x1 minus x2 which is less than delta. This will imply f of x1 minus f of x2 which is less than epsilon. Okay, where x1 and x2 belongs to the interval. So in the definition of continuity, not in uniform continuity, in the definition of continuity, delta usually depends on epsilon or one of these points, okay, say x0. But in uniform continuity, we can say from here that look, it's not x minus x1, okay, so it's not that like for x, like for every x minus a single point, okay, it's a single point minus a single point, okay. So from here we can say that delta only depends on it only depends on epsilon, okay, not on a single point. So now we will head to the proof. So let's say that x1 and x2 belongs to a comma infinity, in this interval, okay. So now we are trying to find the value of f of x1, f of x2, okay. So keep it in your mind that we are trying to prove this x. Keep it in your mind that we are trying to prove this, okay, to prove that or to show that this is uniform continuous, okay, on this interval, okay. So now this will be 1 by x1 square and this will be 1 by x2 square, okay, and this will be x2 x1 square minus x2 square by x1 square x2 square, okay. So now and this will be x1 plus x2 and x1 minus x2, okay, by x1 square x2 square. So now this will be x1 plus x2 by x1 x2 and x1 minus x2 x1 x2, okay. So as we have taken before, x1 and x2 belongs to a comma infinity. So x1 and x2, they both belongs to closed a to infinity, okay. So this means x1 and x2, they might be equal to a or not so. So we can write a is less and equal to x1 and a is also less and equals to x2, okay. And we get if we add these two, it becomes 2a less equal to x1 plus x2 and a square is less or equal to x1 x2. Okay, so now this becomes okay, and this one will be 1 by x1 x2 less equals 1 by a square. So now this will be mod of x1 minus x2 by a square, and this will be 2a by a square, obviously greater equal to. So we get f of x1 minus f of x2 is less equals x1 by x2 into 2 by e cube. Okay, so we get this. Now let us take epsilon. Let us take a positive epsilon such that we took epsilon such a way that it is greater than this. Okay, so now see, we get this actually f of x1 minus f of x2, mod of f of x1 minus f of x2 is less than epsilon. Okay, now we need to define this. So now let delta such that this is equals to epsilon into e cube by 2. So now the question is, okay, so finally we get epsilon for all for any 2 points x1 and x2 belongs to the interval I. Okay, it's not I, it's closed a comma infinity. Okay, if is uniformly continuous on closed a to infinity. Okay, so this is proved. Now we're gonna prove the second part. If x is not, so now we're gonna prove the second part, which is if x is not continuous, not uniformly continuous on open 0 to infinity. Okay. So now for this, let's take x1 is equal to let's say 1 by root n, and x2 is equal to 1 by root n plus 1, where n belongs to like set of natural numbers. So as n belongs to n, so this n will be like 1, 2, 3 and so on. So the value of x1 and x2 cannot be negative. Okay, as this is positive and n plus 1 will also be positive. Okay, so clearly we can write that they both belongs to 0 to infinity. Okay, so as this will be these two will be positive, so x1 and x2 will never be 0, so it will be open 0, not closed 0. Okay, so now what we're gonna do is we're gonna find the value of f of x1 minus f of x2. This will be as f of x is equal to 1 by x square, so this will be n minus n plus 1, and this will be 1. Okay, so now this will be 1. So now here's the trick. We need to prove that this is not uniformly continuous on 0 to infinity. Okay, so now in the definition of uniformly continuous, we were choosing an epsilon. Okay, so now if we choose an epsilon which is 1 by 2, we cannot define this. Okay. So this will be like what I meant to say is this will be like greater than epsilon, then this will not be less than epsilon. So we can straight up write if is not firmly continuous on 0 to infinity. So now but if you want to like evaluate this one, you can So this will be mod of x1 minus x2, which will be 1 by root over n minus 1 by root over n plus 1. This will be root over n plus 1 minus root over n minus root over n by root over n plus 1. Okay. So now what we're doing is multiplying both denominator and numerator with root over n plus 1 plus root over n. So root over n plus 1 plus root over n. So this will be n plus 1 minus n. This will be root over n plus 1 and root over n plus 1 plus root over n. So this will be this one. So they will get eliminated and the value will be this. Now you can straight up write, let's say this equal to p. Okay, as n belongs to the set of natural numbers, so this the value will be positive. Okay, so you can say n is positive, n plus 1 is positive, so this will be, the whole thing will be positive. You can say this is p. So this will be, let delta, which is equals to p. So this will be like, so now the or x1 minus x2 is less than delta, and this implies this is actually greater than epsilon. So this is not less than epsilon. Okay, so this is, so if is not uniformly continuous on 0 to epsilon. Okay. Question number 6b. Prove that if fx is continuous at x equal to a, and for every positive delta there is a point c delta belongs to a minus delta comma a plus delta, such that f of this point is 0. Then we need to prove that f of a is equal to 0. Okay, so first, okay, so let's say a is here. Okay, let's say a is here. So c delta belongs to a minus delta comma a plus delta. Let's say this is a minus delta and this is a plus delta. Now let's say c delta is here, okay, this point. Now this is 0. Okay, now this is 0. I mean, not this is 0 actually, it's f of c delta is 0. So this is 0. F of c delta is 0. We want to prove that this is also 0. Okay. So we're gonna use this property of continuous functions, which is neighborhood property. I be an interval, and if I to R is continuous on I. Okay, let me use this. Okay, let C belongs to I such that f of C is not equal to 0. Then, as f of C is not equal to 0, then either f of C is negative or f of C is positive. Okay, so then for a chosen positive delta, fx keeps the same sign as fc for all x belongs to neighborhood of C delta. Okay, so let's say f is not equal to 0, then fc is negative. Then by this theorem we get a point x1. It's not a point actually, there might be many other points. So there will be like a point x1 such that f of x1 is also negative. Okay, and this will be in like a neighborhood of C. So this will be in this neighborhood, okay, a neighborhood of C. And if this is the case, okay, so let's say fc is positive here now, for now, and then by this theorem we will again get a, let's say, x2 which will be positive, and x2 will be in this neighborhood of C. Okay, so this is the theorem. Now we are gonna prove this. So we need to prove that f of a is equal to 0. Okay, so first we are assuming that let f of a is not equal to 0. Okay. This is not equal to 0. So what's gonna happen? Then either f of a is negative or f of a is positive. Okay, so first we are taking this case. So let f of a is negative. So now what's gonna happen? So f is continuous, f is continuous at a, right? It's continuous at a, as a is, it is continuous at a. Okay, so now what we're gonna get cut. Okay, so now f is continuous at a. Okay, f is continuous at a. So now what we're gonna get is cut. F is continuous at a. See here, fx is continuous at x equal to a. Now what we get is by that neighborhood property, what we can say is for a positive, let's say it is delta 1, or no, let's say it's delta, okay, as it's delta here in the question. So let's say for a delta, okay, so for a positive delta, what do we get? If x will be, as this is negative, if of x will also be negative for all x belongs to neighborhood of a comma delta. So domain is not mentioned here, okay. This is going to happen. So now what do we get? X belongs to this neighborhood, okay. What does that mean? This means x belongs to a minus delta to a plus delta, okay. So now see that c delta also belongs to this interval, okay. So x belongs to a minus delta, a plus delta. So now we will get, as this is for all x, so this will be also true for c delta, as it belongs to the same, like same a minus delta or a plus delta. Then so we can write, this implies f of c delta is negative for all. It's not for all actually. Where c delta belongs to this, okay. So now as you can see that this is contradiction, as f of c delta is equal to 0, okay. So which is a contradiction, as f of c delta is equal to 0. So we are right, as given f of c delta is equal to 0. But what do we get? F of c delta is negative. So this is a contradiction. So our assumption was wrong. So this will be not negative. So our assumption is wrong, and what do we get? F of a is not negative, okay. Now so now we're done with this. Now we're gonna take that one. So let f of a is positive. So now by the, like, it's the same thing. So now if is continuous at a, then by neighborhood property, what do we get? For a chosen neighborhood property, for a chosen delta, f of x will be same as f a, which is positive, for all x belongs to a comma delta. Okay, so now as before, c delta belongs to a minus delta comma a plus delta, okay, which is actually this neighborhood of a comma delta. So as this is true for all x, this also belongs to the neighborhood of this. So what do we get? F of c delta is positive for all, it's not for all, c delta belongs to this. Okay, and again this is a contradiction. As f of c delta is equal to 0. Okay, so our assumption is wrong. This will be not positive. So our assumption is wrong, and f of a will be it will be not positive. Okay, so and we also got f of a is not negative, so it will be equal to 0. Proved. Question number 3b. If a comma b to r continuous function is a continuous function such that f of x is positive for all x belongs to ab, that means if x is always positive. Okay, prove that there exists an alpha which is greater than 0 or a positive alpha such that f of x is greater or equal to alpha for all x belongs to a comma b. Okay, now what does this mean? F of x is greater or equal to alpha for all x belongs to a comma b. This is actually the definition of infimum of fx. Okay, so let's say alpha is infimum of fx where x belongs to a comma b. Then from here what we get, or from the definition of infimum, what we get is f of x is greater or equal to alpha for all x belongs to AB. So see, we get this, actually we get this. So at first we need to prove that alpha is actually the infimum of fx. Then we are going to prove that alpha is positive. But at first we will prove that alpha is infimum of fx. Now f is continuous on AB. F is continuous on interval AB. Okay, so now from here we can say many things actually. Okay, so there are many theorems. Actually, the property of continuous functions, if f is continuous on AB, then by extremum value theorem, then by extreme value theorem, what we get is infimum of fx. So infimum of fx, x belongs to a comma b, and supremum of fx so both of these exists. Okay, and as f is continuous on AB, then from the property of continuous functions we can say that f actually attains this, like f actually attains its infimum and f attains its supremum. So what does that mean? There exists at least one point, we are taking it x0 here, there exists a x0 in the domain of fx such that f of x0 is equal to infimum of fx. Okay, so f is attaining its infimum, okay, which is x0 here. And f is also going to attain its supremum, but we don't need that here, so we are only taking the infimum. Okay. Now let's say the infimum of fx is alpha. Okay, say the value of infimum of fx is alpha. Okay, so now we are going to prove that infimum is alpha. So let me clean here. Okay, so now from the definition of infimum, what we get is so from here what we get is f of x is greater or equal to alpha for all x belongs to a comma b. The definition of infimum. Okay, so this part is proved. This part is proved. Now we are going to prove this here. This part, alpha is positive. So alpha is x0. Alpha is x0. Okay, and which is greater than 0. Why? Since fx is greater than 0 for all x belongs to a comma b. Okay. Then from here we get alpha is positive. Okay, so there exists an alpha positive alpha such that f of x is greater or equal to alpha for all x belongs to a comma b. Proved. Question number 2b. Use the definition of limit to prove that limit x tends to infinity x minus box x by x equal to 0. Okay, so at first we're just gonna see what is the definition of limit at infinity as x tends to infinity. Okay, so it will be limit at infinity. Okay, so let's say there's a function f d to r. Now what we're gonna do is we're gonna take a interval which is c comma infinity, which is inside this domain for some c belongs to r. Okay, so now this limit, okay, so this is equal to L. So now if this thing happens, we can say that for a p assigned epsilon there is a real number g. So there is a real number g, this will be always greater than c, such that fx minus L, which is less than epsilon for all x greater than g. Okay, so first we're gonna start with an observation here, which is mod value of box x of minus x. This is always less than 1. Okay, so let's take an example here. Let's say x is 1.2. Okay, so now what will be the value of this? Box of x is 1 and x will be is x 1.2. so box of now mod of box of x minus x, this will be 1 minus 1.2, this will be minus 0.2, which will be 0. Okay, so now this will be x of minus box x by x, this will be less than 1 by x. Okay, so now say let us choose an positive epsilon, okay, such that actually this thing will be here, actually such that this thing will be less than epsilon. Okay, so now we're choosing g such that this is equal to 1 by epsilon, which is greater than 0. Okay, so now what's going to happen is this thing will be less than epsilon. Okay, for all this thing will be less than epsilon for all x greater than g. Okay, so now how we're getting this? Okay, so first of all from here we can write that x is greater than 1 by epsilon, which is equal to g, so it becomes this. Okay, that's how we're getting this. So now what do we get? And we can write this like this, minus 0 is less than epsilon actually for all x greater than g. So by the definition of limit, this is L here, this is the L of the definition, and this is the fx of the definition. So by the definition of limit, we get limit x tends to infinity, this function here is equals to L, which is this. Okay, so proved. So let us consider this function as fx. So this limit becomes limit x tends to infinity f of x, and this function has gx. Okay, so this becomes this. Okay. Limit x tends to 0 f of x whole to the power gx. Now for this kind of formation of limit, we can use the L'Hopital method. Okay. So there are many different methods, but using the L'Hopital method, I think this will be the most simple one. What I meant to say is, if you see any limit which is in form of this, okay, so I think L'Hopital rule is one of the easiest method you can go for. Okay, for this kind of limits. So we are doing it with the L'Hopital method. Okay, so at first what we're going to do is we're going to take the whole thing as y. So let y equal to this. Okay, now taking log in both sides, so this becomes log of y x log of 1 plus 1 by x square. Okay, now as you can see on the right side, there is no actual denominator. Okay, so like there is actually denominator which is 1, but we cannot I mean, if we differentiate this, we'll get 0 obviously. So like there is no actually like proper denominator here. Okay, so we need a denominator to use the L'Hopital method. So what we're gonna do is we're gonna take x as 1 by z, or we're gonna take z as 1 by x. So let z is equal to 1 by x. Okay, so what do we get? Log of y, this will be log of 1 plus z square by z. Now you see there is a denominator, like if we differentiate this, we won't get 0. Okay. So now take limit on both sides. Limit x tends to infinity log of y. And okay, so we actually can't take limit x tends to 0 here, as both of the numerator and denominator are of function z fz. Okay, so as x tends to infinity, see, as x tends to infinity, so it will be 1 by infinity, then z will be 0, so z tends to 0. Right here, limit z tends to 0 log of 1 by z square by z. Okay. So let me clear this one. So now what do we get? We get limit x tends to infinity log of y is equal to, okay, so now we're putting z equal to 0. This will be log of 1, which will be 0, and z is equal to 0, so z is going to be also going to be 0, so this will be 0 by 0 form. Okay, then now we are going to use the L'Hopital rule here. So what we're going to do in this rule, we are going to differentiate. So now, as it is 0 by 0 form, as it is in 0 by 0 form, we are gonna use the L'Hopital method. Okay. So in this method, what we do is we differentiate both the numerator and the denominator. Okay. So limit z tends to 0 become so now we are going to differentiate both the numerator and the denominator. And what do we get? Limit z tends to 0, differentiating the log of 1 by z square, we get, what do we get? 1 by 1 plus z square, and z square is 2z. Okay, and this will be 1. Okay, now we are putting z equal to 0, so this becomes 1 plus 0, it becomes 1, and it becomes 0, z, and the whole thing becomes 0. Okay, so what do we get? Limit x tends to infinity log of y equal to 0. Okay, so we get these. Let me clear the whole thing. Now limit x tends to infinity log of y equal to 0. which is log of 1. From here what we can write is log of limit x tends to infinity y is equal to log of 1. From here what do we get? So log of this equal to log of 1, so this becomes 1. Limit x tends to y equal to 1, and y is our this function. So limit x tends to infinity 1 plus 1 by x square whole to the power x becomes 1. Hey guys, that's it for today's session. I hope this solution helped you understanding limits, continuity and differentiability better. If you found this video useful, don't forget to like, share and subscribe to the channel for more math contents. Also let me know in the comments if you have any doubts or if there's a specific topic you want me to cover next. Thanks for watching and I'll see you in the next one.